Well, welcome everybody to Stars, Cells, and God. This is a podcast where we explore the scientific case for the Christian faith. My name is Rana. I'm a biochemist and a Christian apologist, and I also work for the organization Reasons to Believe, which is the organization that is sponsoring this particular podcast. So if you want to know more about Reasons to Believe, please visit our website, www.reasons.org, or you can also follow us on social media, RTB_official. And then finally, if you are watching this program on YouTube, please go ahead and subscribe to the Reasons to Believe channel. And then also make sure you set a reminder so that you are alerted to when new episodes of this program and other programs appear on our channel. I'm joined today by Dr. Jeff Zweerink, a friend of mine and a colleague here at Reasons to Believe. Jeff is an astrophysicist and a senior scholar at Reasons to Believe. And both Jeff and I are going to be talking about new discoveries that, again, give credibility to the Christian faith, scientific credibility to Christianity. And both Jeff and I are going to be talking about discoveries that involve biochemistry. So we're going to be in the molecular realm today. Jeff is going to be talking about a protein called kinesin and some pretty interesting new insights into that protein. And I'm going to be talking about the process of how proteins are imported into the cell. And so we're going to be, again, in the realm of biochemistry today. So without any further delay, Jeff, why don't you take over and tell us about the discovery you want to share?
Yeah, well, this is a discovery, about kinesin. Kinesin 1 is the particular name of the molecule, and I know just enough biochemistry to understand what we're talking about. But really, this is talking about the physics of how it moves. And I remember in my biology days, you study biology and wherever you did in high school, and there's the organelles, and you memorize the structure of the various things. But I just know in the number of years since I looked into that in high school, it's like there's just been a proliferation of what we know actually goes on inside the cell. And there are these animations and dynamics. There are tubes that extend, and there are highways that molecules move along, and they move these loads this place and that place, and they absorb through, and just understanding the cell walls. And so, I don't want to, I'm not commenting on any of that, except that as people have looked at one of these particular molecules that is moving loads around the cell, they actually ran across this very interesting discovery. As they were looking at it, it's it's kinesin 1. It is a molecule that kind of walks along these microtubules. And so they had taken this molecule out, put it in the lab, built a glass substrate, put a microtubule on it, and then did measurements of how this molecule walked along. And what they found is as it used ATP, which is kind of, for my understanding, it's the powerhouse, kind of the energy or the gasoline of the cell, if you will, that a large fraction of the energy from the ATP ended up being dissipated as heat. I mean, as much as 80%. And it just struck the colleagues the scientists studying this as very odd, because they had this sense that things inside the cell ought to function far more efficiently. I got a little graphic that kind of shows just what this cell looks like, or what this molecule looks like. That's the kinesin molecule, and it walks along this microtubule. And again, ATP comes in, and it provides, it converts into the ADP, and it provides an energy, and this thing walks along. And what's not shown on this image is that up at the other end, there's a load that it's carrying. And what's also not shown in this image is that this is happening in a rather crowded, dense environment. And so what the particular discovery that I'm going to talk about is looking at trying to get a more accurate picture of how this molecule works inside the noisy environment of the cell, because there are thermal fluctuations going on, and there's actually they realize that there's another kind of noise in there, and it's levy noise, Levy noise. And the way it's described is it's kind of random motions characterized by occasional jolts. And so what this team of researchers did was actually attached a 500 nanometer-sized polymer bead to the end of the kinesin molecule. And what that allowed them to do now is shine a focused infrared laser onto the bead. And that laser effectively works like tweezers and grabs onto the bead. And now that they have this optical tweezer, they can mimic the loads and the molecules and the jostling of the environment in which this thing operates, the kinesin molecule operates. And what they found was that when they replicated this leve motion, this leve noise in there, that the kinesin molecule dramatically accelerated and it became far more efficient. And I just, as I was reading this article, it just kind of struck me as, wow, that is so cool. I mean, just the technology. I mean, you think about that. Take a 500 nanometer size polymer bead, put it in a molecule, and then grab it with a laser so that you can control the load experience. I mean, there's just the technology behind that's pretty cool.
Yeah.
But
the single molecule techniques.
It really is. Yeah. But then now you're also able to show that though this thing that looks very efficient, that I don't know whether it was argued as a bad design in there or got this molecule in there that's not working very efficiently. But what we found is that when we understood how the molecule worked in the environment in which it operates, it's a highly efficient molecule, very well-designed molecule. And it actually kind of reminded me of the SR-71 Blackbird. I don't know how familiar you are with planes, but this is one of the planes that I find fascinating because there's at least one of them that recorded a trip from LA to Washington, D.C., or it may have been going the other direction, but it did it in 56 minutes. So these planes really haul. But when these planes are out on the runway, they actually leak fuel. And it's an intentional design feature because what they know is that when they get up and operating at Mach 3, everything heats up and it expands and all of those leaks disappear. And in fact, if you made it with no leaks on the ground, in all likelihood, it would crack under the intense pressures up in the air. So it's designed to have this inefficiency on the ground because that's not where you're using it. That's just this temporary transition phase to get it up to where it's operating in its environment. And when it's operating its environment, it's lightning fast. It can outrun missiles. It does high altitude aerial reconnaissance, and it's just a phenomenal plane. But it looks inefficient on the ground, and that's what it reminded me of here. Is that when we looked at this in some artificial environment, it looked highly inefficient, but yet when we look at it in its environment, it operates very elegantly and looks like designed. And the question, or I'll throw a question to you because one of the comments that was made in the article was that when they found this 80% of the energy was being dissipated as heat, they looked at that and said, that strikes me as odd. We expect evolution to have made things to be more efficient. Yeah. And as a creationist, I would expect things to be more efficient because I would expect God to have a design behind things. But it strikes me as a little bit odd when we have all this junk DNA, quote unquote, junk DNA in our molecules, that we have a lot of inefficiency in the amount of information in our DNA. So it just struck me as odd to have this idea that we expect evolution to have done this very efficiently. And being as though you play around in the biological realm more than I, how does that comment strike you?
Yeah, and I want to be careful when I answer this, not to disparage, anybody. But it seems to me at times people that espouse an evolutionary perspective oftentimes speak out of both sides of their mouths. And I'm not trying to be disparaging about this, because on one hand, I'll see comments exactly like the one that you note that's in the article, that we would expect evolution to produce these highly optimal systems, or people that are working in biomimetics. Well, evolution has millions of years to fine-tune and explore all this design space and hit upon the best design. So you'll hear those kind of comments. Then on the other hand, you'll hear people make statements like, we don't expect evolution to produce perfection. We expect evolution to produce suboptimal designs that are cobbled together from pre-existing systems that are far from perfection. So you actually see both kind of statements being made, from people that, again, espouse that particular framework. And my view is that the people that are making the point that evolution produces suboptimal systems that are really cobbled together is really a better description of what you would expect
Hmm.
from the evolutionary process, which is unguided, undirected, historically contingent, using pre-existing systems to cobble together new designs
Hmm.
that are constrained by the history, not by the elegance of the design,
Hmm.
where those systems are just good enough to survive. So I would make the same point that you make
Hmm.
are making, and that would be, hey, as someone who sees God as being responsible for the fundamental design of life, I would expect
Hmm.
optimization. I would expect elegance. I wouldn't necessarily think that somebody who holds to an evolutionary perspective would expect the same thing.
Yeah, and that's kind of what I'm wrestling with is, why do you expect this system that is ultimately predicated on do I survive to produce highly efficient and the one something that struck me and kind of give me a little bit of pause of how do we say this and I agree with your sentiment of this is not a pejorative, it's like it's just this odd thing, but it does strike me that this is a system that is very basic. It's like if this doesn't work inside the cell isn't going to function.
Yeah.
And it's not so much that evolution is driving towards optimal designs as it is this is a basic function that if it doesn't work it's going to be and so there's an aspect to where the I can talk about designing an SR-71 Blackbird, but really the only reason I need that is because of war, and I mean there are other kind of unusual environments that necessitate that. And so where you see design in that sort of thing that says, oh, okay, that points to a creator. But if I do, if on more basic day to day things, if I don't have if those things the survivability of day-to-day things drive a little bit more optimal behavior there. So I could see where this is you could expect optimality or high efficiency out of something like this, because if this doesn't work, it has very dramatic and immediate deleterious effects.
Well, and to just build off your point, if you have something that initially emerges and it's generating 80% heat,
Hmm.
you're wasting a ton of cellular resources.
Hmm.
And so you don't have the luxury of going from a really crude, inefficient system evolving towards a highly efficient system, because the cost of having that, inefficient system at the onset is just way too great.
Right. And again, the two analogies that I wrestled with in thinking about this, and I find that this discovery that there's this in the environment, it just functions very well. Again, the Blackbird just struck me as, wow, this is kind of a system that may look efficient, but it does what it's supposed to do really, really well, because it accounts for I'm operating in an environment where if I don't allow for that, it's going to fail. And I've seen that in multiple things in the places where biological or biochemistry shows up in the physics literature, that kind of efficiency of it works well in the environment. But your point, the other point is like, this is a system that is so foundational that if it doesn't work, it just you miss. And it strikes me that when you talk about DNA, there's this kind of simultaneously everything's optimized because that's what evolution does, but yet there's all of this purportedly junk DNA in our genome. And I think that picture, if I'm understanding in my conversations with you, that picture is kind of changing, that we do think the junk DNA actually does carry a lot more function, although there's a big argument about that. But if evolution was really that efficient at getting rid of stuff, I don't see any reason why there should be any junk DNA left. It's like that's
Hmm.
at minimum, it's a extraneous load that doesn't need to be there. If it didn't need to be there, some process would have filtered it
Right.
out, or that's not a good explanation for why this is so efficient. One of the two.
Right. Yeah, and that's a really insightful point on your part, Jeff, because when you think about, a genome harboring vast amounts of non-functional DNA, it's extremely expensive for the cell
Hmm.
to replicate DNA. And so the obvious thing to do would be to eliminate, to streamline genomes, not to harbor vast amounts of content,
Hmm.
and so or vast amounts of sequences that have no content or no value to the cell. So, that thinking, I think, is again reasonable,
Hmm.
from a bioenergetic standpoint.
And just at the end of the day, I found this discovery
Yeah,
fascinating. I mean, the technology of how you
yeah,
do this. I mean, again, I don't know how you communicate the idea of a 500 nanometer sized bead that you can control with a beam of light. But that's just cool. I mean, no
yeah,
matter how you slice it. So,
yeah. Well, just something, when I look at the video, I think it's worth playing the video again if we can pull that off here. Uh, you know, a lot of times I see people, will show some kind of video like this because
mhm.
this is just an incredibly cool molecule in
Right.
terms of the way it moves. It's just fascinating. It looks like it's almost, you can easily personify this, as walking along the microtubule, but what's interesting is that the movement of the molecule is driven by something called a Brownie and Ratchet.
Hmm.
And I'm pretty sure you're familiar with Brownie and Ratchets, but people, I think, should be aware of Brownie in motion, right? So the example would be like a pollen grain that's dispersed or suspended in water that you're observing under a microscope, and occasionally you'll see that pollen grain just dart,
Hmm.
and what's happening is the molecules that are colliding against that pollen grain more often than not are going to come from uniform directions, and so
Hmm.
statistically there's no net force on that pollen grain as it's suspended in water. But just because of statistical effects, occasionally you'll have more collisions on one side of the
Hmm.
molecule than the other, and that will cause it to move
Right.
until
Well,
the
well, that's what you see. I think the place where people have all seen that is if you've ever been in your house looking at the light shining in the window, you'll see those dust molecules floating around in there. The reason they're moving the way they do is because of the Brownian motion. So it,
okay,
it,
that's
it is
another great.
actually something people have seen. So,
Yeah, yeah. So another great example. So the idea here is that in nano systems, people that are trying to build nano systems at a molecular scale, one of the big problems is how do you actually generate controlled movement?
hmm.
And there was this idea of a Brownie and Ratchet where you're using energy to create directional movement, but that energy is in the form of a barrier that prevents diffusion
Hmm.
in certain directions and only allows diffusion in other directions. And so by putting in place these energy barriers, you can get molecules to directionally move
Hmm.
in a controlled manner in the direction you want them to go. And that's essentially what's going on with kinesin. It's a Brownie and Ratchet, where you have, where the one of the heads binds to the microtubule, and then the other one is kind of floating around randomly, but its movement is constrained by the molecule itself. So
Right.
eventually it'll bind, and so the energetics of the binding
Hmm.
are what create the energy input into the system.
So, so this isn't. I mean, the way it's portrayed is this. The one that's yellow there. It lifts up and it says, oh, "Okay, I need to move
Right.
forward," and does that. In reality, there's a constraint of what it can happen. It can't move one way. It can only move this, and so effectively, the random motion drives it up to the next place where it binds.
Yes.
That's cool. I did
Yeah,
not know
and
that.
and then again, the binding and debinding are going to fluctuate.
Right.
So
Okay.
so over time, you get this directional movement.
Mm.
But what's interesting to me about this is this interplay between the technology that we would invent, at a
Hmm.
nano scale, and then the technology that you see evidenced in the way the molecules operate. So
Right.
there's this interesting interplay between our technology and the technology we see in biochemical systems. You know, and so when you think about the idea of a Brownie and Ratchet, I think the idea was proposed in the 50s by a physicist.
Okay.
as a conceptual idea,
Hmm.
right? And so it's only been recently implemented in nanotechnology. But what's fascinating is here we see that technology being exploited by the cell,
Right.
well before anybody even conceived of it. And so when we looked at the movement of kinesin prior to the use of Brownie and Ratchets, nobody would have even understood that it's actually, again, a model for the technology that we would use.
Well, yeah, and that sort of recognition is fascinating to me because um we're increasingly, whether this was, we see Brownie in motion and we designed that or not, but we are kind of increasingly looking and seeing, oh, this is what nature does, we can do. I mean, that's, we've been
Right.
talking about flying, and so we looked at birds and said, can we mimic that motion? That there's a recognition that nature's doing something we can't, and we're trying to up our game, if you will, so that we can do it. And
Yeah.
it's just kind of interesting to see that in reverse, where we generate something that we think is novel, and lo and behold,
Yeah.
nature's
Right.
already figured, quote unquote, nature has already
Yeah.
figured out how to do it.
Yeah. Well, in my book, The Cell's Design, I talk about the similarity between the technology in the cell and the technology that we invent,
Mhm.
and use that to make a watchmaker argument. But there's kind of variations of the watchmaker argument. Like I made something I called a watchmaker prediction, where,
Mhm.
I said, well, look, if this is watchmaker argument is really valid, then as we invent new technologies, the prediction would be we should discover that
Right.
inside the cell that technology already exists. And
Mhm.
and then likewise, if kind of the current converse watchmaker argument that if the designs in biology are really created by God, then we would expect that they should serve as a source of inspiration for our
Right.
technology.
Right.
So again, it's just this interesting interplay between the technology in the cell, the technology we invent, and then thinking through how can we use that interplay to
Mhm.
to construct an argument for God. So anyway,
Yeah, well, and the one last point about that comment that I wonder if is true, and I'm not, I try to be pretty careful about ascribing motives, but it does seem like, when I, as a person who believes that God created life and who works on things that I don't understand at times, and it's like, why is this? I've had enough times where I've been working and it's like, oh, okay, that's why it's there. That what I thought was stupid turned out to be my lack of understanding of things. And so I would expect that we are going to look at nature and we're going to find things to be very well designed, that they work the way they do, especially when you account for the fact that these are not built in the lab things. They're designed to work in very noisy,
mhm.
what you might even term dangerous or hostile environments, and yet they work very well. The idea that everything works efficiently and well designed seems to be something that, at some level, the naturalist is borrowing from a theistic worldview,
Yeah.
there's a prevalence of, just the way the West at least has thought over the last 100 years has been very much kind of in the Judeo-Christian way of thinking. Not that you had to be a Christian to do that, but that's kind of the ethos of, or the way we think about it, if you will. And so it seems like it does kind of seem like that statement of we expect biomolecules to be adapted or by evolution to do their job efficiently. Um, if evolution works the way I think it, those molecules do it well enough to survive, and anything beyond that should appear weird. And so, again, 80% inefficiency, you could be argued that's not well enough to survive, but it seems like that idea of efficiency is something, or efficiency or optimality is something borrowed from Christianity or a theistic worldview rather than part of the worldview.
Yeah. 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 I think that's an excellent point. That and what I also see too is that when you actually see biologists reason consistently with an evolutionary perspective on things, many times when they see designs they don't understand, they are quick to view them as being just flawed designs
Mm,
or are cobbled together or some kind of vestige of an evolutionary history. And it's oftentimes much later in investigating that system where somebody, uh, in spite of the paradigm, as opposed to because of the
hmm.
paradigm, actually discovers a rationale for why things are that way. And then suddenly what has been declared to be a bad design suddenly now looks like, again, it makes sense.
Right.
And so, I see it, the influence actually that going both ways. And it's kind of similar to the point we've been making. It's almost as if you see evolutionary biologists having really a double mind on the nature of biological systems. So.
Well, I know you've got a discovery related to, but different. So
Yeah. Well, there's some interesting points of connection that people will see, I think. And I love how you use analogies to help people grasp sometimes some technically obscure points. And so hopefully I can do the same thing. But one of the enduring images I have of 2021 is all those cargo ships off the coast of Southern California, right? Waiting to unload their cargo at the ports of Los Angeles and Long Beach. And I've learned that 40% of the imports into the United States actually go through those two ports. They're the two largest ports. So apparently we import about $2.8 trillion worth of goods into the United States. So that means like $1.2 trillion worth of stuff goes through those two ports. And people are trying to dissect what went wrong. Why was there this backlog? And because it just created havoc for our economy. There were things you couldn't get on store shelves that you would just assume would always be there. It was a little bit disquieting in some respects. Well, part of the assessment is that, consumer habits changed very rapidly because of COVID, where people were not going out to eat or going to movies or music venues or sports venues. And so they were taking that disposable income and they were buying stuff with it.
Okay.
And that created this incredible demand that then caused people to begin to place orders for goods, and because it happened on large enough scale, you didn't have the capacity at these ports to handle all of the goods that were coming in. But then because of COVID too, you didn't have full crews at the ports, and you didn't have the people to haul stuff away. And so everything kind of, all at once, it was a perfect storm of not having the capacity at the ports. And then when you up the number of dock workers, you still didn't have warehouse space. You didn't have the truck drivers to move things. And so the whole point is that if you don't have a highly efficient, highly integrated system for importing goods into a country, things can unravel quickly. And this is the same principle that we see when it comes to the cell as well, is that cells have to move things around. You have this, your example of kinesin is an example of a system moving cargo around inside the cell. But sometimes cells have to import things across borders inside the cell or cell membranes or the cell boundaries. And if that import process isn't working efficiently and effectively, it can create all kinds of problems, just like not being able to import goods into the U.S. cause problems for our economy and probably economies around the world. And this is particularly true when it comes to mitochondria. And these are these tiny bean-shaped organelles. This is an image of a mitochondria that serve the cell as, in a number of ways. One is that it provides energy for the cell to use. So it's the organelle that's producing most of the ATP inside the cell. So the ATP that powers the movement of kinesin is being produced in mitochondria, and it also serves as a metabolic hub where it is essentially generating compounds or at least generating intermediates that are part of pathways that are needed to make building block material. So it's a very important organelle. And a typical cell will have thousands and thousands of these organelles. And if something goes wrong with the mitochondria biology, it's bad news.
So the cells have many mitochondria, or a cell will have one mitochondria in amongst a whole bunch of other organelles?
No. It'll have thousands and thousands of mitochondria.
One cell will.
One cell
Oh,
will.
okay. All
Yeah,
right.
yeah, because they're so important.
Okay.
Right. But there's a whole set of diseases called mitopathologies,
Mm-hmm.
or sorry, mitochondrial pathologies that are uh, due to essentially some kind of breakdown in the
Okay.
mitochondria.
All right.
And this usually leads to neurodegenerative disorders
Okay.
when that happens. And there's probably 200 or so mitochondrial diseases
Mm-hmm.
that are known. Well, protein import is really important for mitochondria because there's about 1,000 different types of proteins inside mitochondria that are carrying out specific functions.
Mm-hmm.
And of those proteins, many of them will have multiple copies. So there's thousands and thousands of proteins inside mitochondria. 90% of those proteins have to be imported into the mitochondria. They're actually made in the cell cytoplasm, and then they have to be imported into the mitochondria. Now, there are about 10% of the proteins in mitochondria that are actually produced in the mitochondria itself. Mitochondria have this little, and you can actually see that in the diagram, this piece of DNA that
Okay.
encodes for some mitochondrial proteins. And so the question would be, well, why aren't all of the proteins encoded in the mitochondria instead of being encoded in the nuclear genome and then made in in the cytoplasm and imported? It seems like at first glance it would make more sense for everything to be imported or be produced in the mitochondria. Well, it actually turns out, and I won't get into the reason for this, that it's actually energetically more efficient to encode proteins in the nucleus
Okay.
and then have it made in the cytoplasm and imported into the mitochondria. It's actually a more energetically efficient way of doing it.
Okay, so you've got a single nucleus that has the coding for a whole lot of these proteins. The cytoplasm, which is kind of presumably spread throughout the cell, takes care of generating all these proteins, and then
Right.
the multiple mitochondria that are within the cell import that in and do
Right.
some function with it.
Right.
That's the picture.
Right.
Correct? Okay.
Right. Now, the process of importing is complicated because not only do you have to actually target the protein to go into the mitochondria, because there's other proteins that are being made that are going to have other use in the cell. So, there has to be a mechanism, we'll get into that, to target the protein to the mitochondria. But it's more complicated than that because once you target it to the mitochondria, you have to sort it to the right location in the mitochondria. And so in
Okay.
that diagram, you see that there's an inner and an outer membrane.
Right.
So some proteins are embedded in the outer membrane, some are embedded in the inner membrane, some actually exist in the intermembrane space between the two membranes, and then some have to go into the lumen or the matrix of the mitochondria. So you not only have to get the right protein to the mitochondria for the import process, it's got to go to the right location, just like you have truck drivers that take the cargo that is imported and then delivers it to the right warehouses throughout the country.
Okay, so part of the problem is there's far more proteins in the cell than what the mitochondria need to use. So you've got to get the right proteins to the mitochondria. Right. But beyond that, it's also not just, you can adhere anywhere or be
Right.
anywhere. It's got to be in the right location. So does the mitochondria sort that, or does the movement through the cell sort that out somehow?
Well, it's a combination of both.
Okay.
And what happens is that proteins that are targeted for the mitochondria have something called a signal sequence at one of the ends, at the N-terminus end, and it's like an address label. It tells the cell's machinery this protein is to go to the mitochondria.
Okay.
And then once it gets there, there's this is a very simplified diagram where you have.
So, but before you go on, what's reading the address?
I'll get to that in a
Okay, all right, I'll get that into my question then. So.
Yeah, and I don't think we completely understand, but we do have some glimpses as to how that address label is read.
Okay.
But so once it gets there, there's a complex called TOM, which stands for the translocase of the outer membrane.
All right.
And so TOM, if that, it will bind that protein, And if it is to go into the outer membrane, it'll shuffle that protein to another complex called SAM. And I don't remember what SAM stands for. It's like sorting accessory machinery or something like that. And then if it's going to go into the lumen, Tom will pass that protein to another protein complex in the inner membrane called the translocase of the inner membrane, or TIM, but it's actually, there's different TIMs. There's
Right.
TIM23. If it is to go into the inner membrane, then there's a TIM22 that will take it into the inner membrane.
Mhm.
If it is to go into the inner membrane space, it's not shown here. There's another complex called OXA or TIM22. Both of those can get it into the inner membrane space. Sometimes a protein will have a second sequence called a stop sequence that once it gets into the inner membrane space will block it from going into the lumen, and it'll reside in the inner membrane space. So there are multiple pathways that help sort proteins as they go into the mitochondria.
And at the end of the day, this is all just effectively chemical bindings and attractiveness to things. So presumably this molecule comes in, whatever the protein is, and it interacts with the TOM, and it either binds well or it doesn't. And if it doesn't, it's something else. And if it does,
Right.
then Tom... It has this imagery of Tom saying, this is where it goes, but it's really just, these are the chemical bindings that are going on at the end of the day.
Yes.
Okay.
So here's a little bit more detail now. So, and we're just going to focus on the left-hand side of this diagram. So here you see the protein.
You do realize the left-hand side is the complicated side.
Yeah, unfortunately. And so you can see where the NH3 plus, that's the N-terminus end, there's the let's see here, that's where the signal sequence is. But in the signal sequence, there is something that targets it to the matrix. There's another place where it targets to the inner membrane space. And so here we can see TOM, and the TOM is actually a massive protein complex. There's a whole bunch of subunits that are part of TOM. Many of them are not shown there, but TOM20 it recognizes that signal sequence.
Okay.
So when it binds the signal sequence, it will then kind of shuffle it into a channel in TOM40, and that channel actually is somewhat contiguous with the TIM23, so it moves right through the two channels into the matrix, and then there are enzymes called proteases that'll cleave away that signal sequence. So if in some instances that protein will just fold and play its role in the matrix. And by the way, this is actually a Brownie and Ratchet. Because there are these proteins called chaperones that are not shown here that will bind the protein as it comes through the channel in TOM and kind of pull it through.
Right.
And so it's like a Brownie and Ratchet where you're preventing the back diffusion of the protein. But it's all diffusion that's taking it through the channels, coupled with, again, chaperones binding and preventing the back diffusion from taking place.
So this strikes me as an incredibly complex system because, you said, it's TOM, but TOM turns out to be, there's at least 3 members of TOM here.
And there's a lot more that
I'm assuming
shown.
they didn't choose those randomly numbers, that there's probably close to 40. That's why we get up to 40. So is like TOM always sequentially this way, or TOM randomly, could the ordering and the distribution be different? Or is that kind of, for TOM to function properly, it's always this way, kind of like your supply chain. There's always the cargo ships and the dock and then the trucks and the warehouse and
Okay. It's not, it's a complex of protein subunits that bind together and then kind of stick together within the membrane. So there's like a region in the membrane where you have different TOM complexes.
And so presumably the TOM on the top and the TIM on the bottom, there's not only the complex up here that has to work, but it has to align properly with the stuff in the inner cell.
Yes, exactly right. And then again, as we talked about, there are, we're not seeing it in this diagram, but there's, again, TIM and OXA, which would, if there is a sequence that indicates it should go in the inner membrane, there's a TIM22 that will get it into the membrane. OXA will get it into the membrane. They're operate with slightly different mechanisms. Both of them can also import it into the intermembrane space. And then SAM's not shown here as well in that diagram. And then on the right, sometimes you'll have a stop sequence that once it's imported, it just simply won't go through TIM23 into the matrix. It stays there. So again, the whole point here is that there is a complexity to this process, right? Where it's not just simply targeting it, to the mitochondria for import, but then there's a whole elaborate set of mechanisms that are working collaboratively to get the proteins in the right spot. Now, this brings us to the new discovery. Okay.
That's not the, no.
Yeah. So this is setting the stage. So it turns out that there is a protein that it's called DYRK1A. All right. So that's the name of the protein. And we have learned that mutations to the gene that encode that protein are part of the etiology of things like Parkinson's and Alzheimer's. But nobody quite understood why that was the case. Well, it turns out, long story short, this particular protein is called a kinase, which means it attaches phosphate groups to other proteins.
Okay.
And this DYRK1A protein actually will add phosphates to a protein called TOM70, which is actually part of the TOM complex. But TOM70 isn't tightly associated with it. So you have the TOM core, where all those subunits are closely bound, and then TOM70 is kind of sliding around, moving around. When it's phosphorylated, TOM70 will form a tight association with the TOM core.
Okay.
And when that happens, it opens up the gate, allowing for protein import, right? And if it's dephosphorylated, TOM70 dissociates from the TOM core and protein import stops. And so this discovery...
So the TOM, without TOM70 binding, the rest of the TOM complex really doesn't allow much into the...
Right.
So even though it's not associated, or it's not bound to, it is critical to the functioning of it,
right.
It sounds like.
Right. So people thought it was just once you had TOM20 binding the signal sequence, it was an immediate import passively into the channel. And now we know that there's actually a process regulating the import. So the analogy would be, hey, if I'm importing particular goods into the United States, let's say lawnmowers,
right.
And there's an overabundance of lawnmowers, in the country, then I'm going to stop the process of importing them until we sell some of those lawnmowers, and there's actually a need. And that's the same idea, is that the mitochondria needs to respond to different things happening in the cell, the energy status, other metabolic stressors in the cell. And so sometimes the mitochondria needs proteins, other times it doesn't. And so this is a mechanism that regulates the import into the cell. But the whole idea here is that we now have an expanded understanding of the process of protein import, and it's just becoming even more complex as we learn more about it. But what's interesting is that there's an analogy between what we see here, and again, what happens when you're importing goods into the country, right? First of all, you've got to have a port. That port has to be equipped to receive, ships. You have to have a means to unload the ships. You got to have a place to store that cargo, a place then to get that cargo to warehouses, and then a means to deliver that cargo to other warehouses. So it's a set of complex operations that have to be precisely integrated with one another for that process to work. And in the same way, what we're looking at here is a collection of complex processes. You might say they're irreducibly complex processes, where all those processes have to be simultaneously integrated to one another. And so, and again, you've got a Brownie and Ratchet mechanism undergirding this. So there's another analogy between the way that we construct systems and the way that biochemical systems are constructed. So there's a theme here that's emerging, is that there's, again, this analogy between how we would, put in place very complex processes that are highly integrated in what we see inside the cell. So this, to me, again, is a pointer to the work of a creator. It's not just that this is an incredibly complex
Mm-hmm.
process, but there's also an elegance and a sophistication and an ingenuity to it. But on top of that, it's an integrated complexity, which again is analogous to the way we would design systems. So if we
Mm-hmm.
think about design being not just simply creating devices, but also creating systems,
Right.
we again see a place where we can make another type of watchmaker argument.
Well, and that's what struck me is like there's this. Not only is it do we build systems like that, and so okay, we're seeing a system like that, but kind of going back to my comment that this is all driven by chemical bindings. That there, in all of our systems, there's two aspects. One, there's the person or group of people who've designed the system, but then there's always a mind. Is the system working properly, and what needs to go on? This system, just quote unquote by the laws of physics and how atoms attract one another, is self-regulating.
Yeah.
I mean, the building the system that works is incredible in the first place. I've done enough stuff trying to make things work independent of whatever might come at them. That is really hard. And this, your ship analogy, there's somebody out there saying, wait a second, we've got too many lawnmowers. Whereas if I get what the Tom 70 is, at least part of its function is to say, I know what's going on out here and this is not the time to do it, but it's not cognitive. It's built into the physics, if you will. And that is incredible.
Well, and so the DY, RK1A protein is kind of what is alerting by phosphorylating or dephosphorylating the Tom 70. And I'm sure it's integrated into another metabolic network where it's receiving signals that are giving it information about energy status of the cell or, again, other metabolic demands. So, it's this incredibly elaborate system where we're just presupposing mechanisms that in and of themselves are absolutely remarkable when you think about it.
Yeah. And I mean, just given my, thinking about, just how well carbon performs as a molecule to build long chain molecules, how well water works as a solvent and everything. It's, at the end of the day, if all of those chemical bindings you're talking about are predicated on things that align with carbon and oxygen and water doing what it's supposed to, which, so in some sense, this argument is tying that design functionality back to the intricacies of the laws of physics. It's not just kind of, biology searched around and found what worked. It's actually fundamentally tied to the laws of physics, which we don't get a chance to try multiple ones of those. It is what it is, if you will. This is pretty fascinating.
It is. Okay, one other point. I know we're probably going a little bit long, but one other point, and then we'll bring it to a close real quickly here. And that is that this insight, to me, actually undermines the evolutionary model for the origin of eukaryotic cells. The cells we're talking about are called eukaryotic cells or complex cells. They're the types of cells that we learn about in biology with a nucleus and all these organelles.
Right.
But one of the outstanding questions in evolutionary biology is how do these types of cells evolve? And the model is called the endosymbiont hypothesis, and it's kind of illustrated here. And the idea is that you had this mother cell, if you will, that was essentially engulfing smaller bacteria.
Right.
And those bacteria form these permanent endosymbiotic relationships with the mother cell where they would provide a benefit to the mother cell and the mother cell would provide a benefit to them. But over time, they underwent, these individual independent microorganisms underwent kind of a de-evolution and became organelles that served the overall collective's needs. And the organelle that is emblematic of the endosymbiont hypothesis would be mitochondria. And so this is a diagram that kind of envisions how maybe that evolutionary process might happen, where you have some kind of mother cell again that picks up basically a bacteria that's gram-negative alpha proteobacteria that essentially gives up its parts of its genes that, it just jettisons genes from its genome that are picked up by the nuclear gene. And then over time, a mitochondria emerges and its modern day role inside the cell. So that's the evolutionary model in a nutshell. Now, there's a lot of evidence that people will point to that seem to give credibility to this idea. Mitochondria about the same size as alpha proteobacteria, double membranes, it has a piece of DNA, inside the mitochondria that's a vestige of this evolutionary history.
So it's not a ludicrous idea. I mean, it's a plausible idea, or at least there's some appearances that make it seem reasonable. Yeah.
Yes, and I would agree. And yet, when you start peeling away some of the layers and start asking the questions, well, what would it take for this to actually happen?
Right.
Now you're looking at a process like protein import, because now what you're having to say is that 90% of this endosymbionts genes were taken up by the nucleus. They happen to be the just right 90, genes, or 90% of those genes, the just right 900 genes, where the other ones that were retained were the just right ones that need to be retained inside the mitochondria. All of these genes now had to somehow acquire a signal sequence that would be appended to the genetic material. And that signal sequence was just right to be able to be recognized by Tom, which, by the way, had to evolve from scratch, right? Tim had to evolve, Sam and Oxa and all of these had to evolve at the just right time, the chaperones, the proteases, and they all had to themselves be targeted for import into the mitochondria. So you have all these incredibly just right things that have to happen practically simultaneously for protein import to take place. And so it's again going back to the analogy of importing goods into the country. If you ran a trucking company, you were not going to build a warehouse by the beach, and then hire drivers to carry goods from that warehouse near the beach if it's not near a port, right? The only reason to do that would be if there's actually a port where there is a means to unload cargo from the ship, right? And so every aspect of that process of importing, it only makes sense to establish it if all the other systems are being established at the same time. So when you're dealing with a system that displays integrative complexity, it all has to come together at once, for it to function. And you can't get things happening in isolation. It just you would go bankrupt if you put in a crane to unload cargo from a ship if there weren't ships coming to that port. So.
Well, yeah, and I mean, I look at that in terms of analogies in terms of, when we develop ports, I mean, people that first sailed ships is like, oh, here's a good port because it's good for the ship or whatever. And eventually you're going to start build a road out of there or, build a pathway to, well, this isn't the greatest place to have a house, so we're going to move it, a mile inland or whatever. So you're going to start doing that. So kind of there's that primitive level. But when you start talking about the types of supply chains you're talking about, it seems that's beyond just okay, we're going to take advantage of the environment. There's now this planning and orchestration.
Right.
And the fact that we're seeing things that look like planning and orchestration, you don't get from Plymouth Rock to LA Port without very intentional behavior. It strikes me that you don't get from the engulfed thing to our modern cell without orchestrated behavior. I mean,
yeah. Well, and again, let's run through a scenario. Suppose, there's, it's not surprising that you might an endosymbiont might give up some of its genes. That makes sense, and it's not surprising that some of those genes may be taken up by the nucleus,
right?
Or by the nuclear genome. But now this is where the problem arises, because if that mitochondria or that pre-mitochondria needs that protein, unless this entire assembly is in place, there's no way it's going to get that protein. And so it's not going to be able to survive long enough for this entire integrative system to emerge, right? So you eventually reach a point where, yeah, evolution can explain maybe some of the steps, but
Mhm.
while you're waiting for everything else to come together,
Right. Yeah.
that pre-mitochondria is not going to survive, and it's not going to be of any use to the cell.
Mhm.
So there's selective pressure that you would think that would in fact prevent this. Now, this idea that how do you explain the evolution of protein import into mitochondria as being problematic to the evolutionary paradigm is not just simply something I concocted.
Right.
But there's actually people that are evolutionary biologists that have identified that
Mhm.
problem. One of them is a guy named Franklin Harold, who in his famous book on the cell, classic work on the cell, he talks about the evolutionary origin of eukaryotic cells. And he says the origin of the machinery for protein import is more complicated. And this is more complicated than how do you explain ATP transport, the emergence of ATP transporters, and is subject to much debate. Most of the transferred genes continue to support mitochondrial functions, having somehow acquired the targeting sequences that allow their protein products to be recognized by Tom and Tim and imported into the organelle. So the evolutionary model is this is complicated.
Mhm.
This is a complicated problem.
Right.
And somehow this all happened,
Yeah.
right? And this is not to be, again, belittling
Mhm.
of Franklin Harold, who I have enormous amount of respect for, but rather it's simply to say that nobody really knows how something like this could actually evolve.
Yeah.
And so there's just this faith-like commitment that somehow evolution did it. And it's just, maybe it's an impenetrable scientific mystery. But when you start to probe or speculate how it might have happened, it's very difficult to envision a workable pathway, a workable sequence of events. And given, again, that this is an integratively complex system that's similar to how we would design comparable systems, to me it makes more sense to think of, the origin of mitochondria and really the origin of eukaryotic cells as the work of a creator.
Well, and it seems like, when the endosymbiont hypothesis was put forward, it's like, okay, yeah, it's reasonable. There are some appearances it looks like this might be, but there's a whole lot of things that we assumed were going to get resolved as we started looking into that. And it seems like the more we know, the more it's like, okay, initially it looks reasonable, but there's this not just complexity, but efficiency, intelligence, design behind it that make it really hard to continue thinking that way. That the advancing discoveries really do fit more comfortably in a creationist scenario than in a naturalistic scenario.
Yeah, I think so. Well, I think we've done about everything we can do today. So hopefully people aren't overwhelmed with the biochemistry. But sometimes the details are where you really see the powerful evidence for design. Jeff, thank you so much. I enjoyed our conversation today. Hopefully people watching have enjoyed it as well. Remember to subscribe to the Reasons to Believe channel. Set a reminder so that you get alerted to when new episodes of Stars, Cells, and God are posted. And then last but not least, don't forget to follow us on social media, RTB_official, and check out our website, reasons.org. Until next time, remember, the more that we discover about science, the more that we have reasons to believe.